So welcome back. So having identified the main terminology that we'll be using in the course, we are now ready to describe how symmetric encryption works. And I think that this is the part where the course starts becoming more interesting. So let's see the basic algorithm, the basic idea behind symmetric encryption. Again, we have the same scenario where Alice wishes to share a secret with her friend Bob. And to do so, they will have to use two algorithms. E for encryption and D for decryption. So these are two functions that take an input and output a result. So for the encryption, Alice will have first to generate the secret, her message, a plain text message that she wishes to send to Bob, and she will give this plain text message as input to the encryption function E. In addition to that, Alice will generate a secret key, which is like a password, okay, which will be also give us input to our function E. Now the output, by giving these two inputs to our encryption algorithm, the output will be a ciphertext that will be generated and will be sent by Alice to Bob. So the encryption function takes as input the secret key that was generated by Alice, as well as a plain text message M, and generates a ciphertext C that is sent to Bob. Upon reception, Bob will have to use the decryption function in order to recover the secret that was sent by Alice. To do so, he will give as input to the decryption function the ciphertext that was sent by Alice, as well as the same key that was used by Alice to encrypt her secret. And by doing this and running the decryption algorithm, Bob will basically manage to recover the message that was sent by Alice, and thus find out the secret that Alice wishes to share with him. Now, why we call this a symmetric encryption algorithm is simply because both parties, both ends, they use the same key. So the key that is used for encrypting a message is also used for decrypting a message. So no different keys, right? So with one key, we both encrypt and decrypt the message. Good, so let's see a definition, a more formal, let's say, definition of the symmetric encryption setting. So a private encryption scheme is defined by a tuple of three algorithms, the generation algorithm, the encryption algorithm, and the decryption algorithm, such that the generation algorithm is a probabilistic algorithm that takes as input a security parameter lambda and outputs a cryptographic symmetric key. Now, the finite set of all possible keys that the generation algorithm can output is called the key space and is denoted with calligraphic K. We explained this in the previous video as well. Now, we denote this algorithm with gen that takes as input 1 at the power of lambda and outputs our secret key K. Now, a probabilistic algorithm is, it means that every time that we give to this function the same output, okay, the same input, we will be always getting a different output. Okay, it doesn't matter how many times we will be running the algorithm, the output should be always different, kind of random. So if, for example, an adversary cannot guess what the output of this algorithm will be. Now, the encryption algorithm takes as input the key K that was generated in the previous step, as well as a message, a plaintext message M, and outputs a ciphertext C of M. Now, the encryption algorithm is deterministic, which means that every time that we run this encryption algorithm by providing it with the same input, K and M, then the output will be always the same. Now, we denote this by C of M equals to encryption of M with a key K. Finally, we've got the decryption algorithm, which is again a deterministic algorithm that takes as input the same key that was used for encryption and the ciphertext that was generated in the previous step, C of M, and outputs the message M. We denote this by M equals to DC with the decryption of C of M with the key K. Now, the deterministic algorithm means that always, every time that we run this algorithm by giving it the same input, the same K and the same message, the output will be always the same. Now, about the decryption, keep in mind that it must always be a deterministic algorithm, right? Because we must recover the plain text correctly. Okay, so we cannot have any kind of randomness there. While for the encryption algorithm, in the symmetric encryption setting, it is deterministic, but as we will see later in the course, in the asymmetric encryption, the encryption algorithm is probabilistic, which means that the output will be always different, even if the input is the same. Good. So symmetric ciphers. Basically, an encryption algorithm or cipher is a means of transforming plain text into ciphertext under the control of a secret key K. And it can be either stream cipher or a block cipher. So the stream ciphers, the characteristics of the stream ciphers are that they use short keys and they have only practical security. The encryption is taking place in small quantities, bit by bit. Basically, we encrypt each one bit at a time. There is no error propagation, and they are extremely fast to run. Okay, so they are very, very efficient. On the other hand, block ciphers, they do not encrypt bit by bit, but they split our message into blocks, and they work on a block at a time. So each block is encrypted and decrypted. Typically, the blocks have a length of 64 or 128 bits. So let's see some examples of stream ciphers. So a stream cipher encrypts bits individually, as we already said. So let's see a simple example where the encryption algorithm is basically simply takes as input Si and Xi and equals to Xi plus Si modulo 2. Now, the first thing that you might notice here is that instead of using K and M, we are using Si and Xy. We'll see why. Now, the output of this function we denoted by y of I, right? And this is the encrypted version of xi, right? So si is kind of our key, and xi is basically part of our message. Now, the decryption algorithm works similarly. It takes as input the same key, si, and the output of the encryption, yi, and it is equal to yi plus si modulo 2. Now, why si and not k? So as we already mentioned, in stream ciphers, the encryption is taking place bit by bit, right? So, which means that we need to individually encrypt each bit, and to do so, we need to first generate our key and then split our key into shares, right? And each share of the key will be basically will be 1 bit long. That's why we call these parts of the key SI, okay? And then XY is just a share of the message, because the message also is split it into individual bits. And now, why encryption and decryption are exactly the same operations? Simply because the mode addition and subtraction are exactly the same operations. Good. So let's see an example. Let's say that our message X is 1001, and then the key and its source is 0101. Then if we use the above encryption scheme, basically 1 plus 0 mod 2 equals to 1, 0 1 equals to 1, 0 0 equals to 1, 1 1 equals to 0. So so basically we managed to encrypt the plain text that we see on the first column with the key that we have on the second column, and the third column basically shows the encrypted version of X, like the ciphertext. Now, what you should notice is that, first of all, every time that we do the modulo operation, the mod 2 operation with 1, basically the bit on the X column is flipped. So 0 plus 1 mod 2 equals to 1, so 0 is flipped, and 1 plus 1 modulo 2 equals to 0, which means that the bit on X4 is flipped again. On the other hand, if we do the same with 0, then the bit on the first column remains always the same. This table is also known as the truth table. Now let's do an exercise. Let's try to generate a key and decrypt the letter A using the stream cipher we just described. To do so, the first thing that we need to do is to basically look at the ASCII code of the character that we wish to encrypt, right? So in our case, our character is A, so we need to go down to the table, find the binary representation of letter A, and then encrypt it. So in our case, the binary representation of A is 0, 1, 0, 0, 0, 0, 0, 1. Okay, and then what we need to do is that we need to generate a key in order to encrypt this character. So we generate randomly, let's say, a key in this form 0111 0010, and then we just calculate the modulo addition operation, as you can see in the box on the top of this slide, and the result will be 0011 0011, and this is basically the ciphertext of letter A by using the key that you see here in your screen. Now, in order to see the ciphertext, to translate the ciphertext, we need to use again the ASCII code, and if we look at the ASCII code, we can easily identify that our ciphertext basically is equal to the character 3, to number 3. So basically we managed to encrypt A and transform it to the number 3. Now, OTP, what does OTP stands for? So usually when I do my lectures, I'm quite interactive, so I keep asking a lot of questions with to the students. Now this is kind of impossible, but anyway, whenever I ask the students what does OTP stands for, usually, if not 100% of the times, they tell me that OTP stands for one-time password. Well, this is not false, but in the field of cryptography, OTP stands for one-time pad, which is a perfectly secure stream cipher. I will explain a bit later what perfectly secure means. So let's see how it works. It's pretty similar to what we described in the previous slide. So we have again an encryption and decryption algorithm that takes as input a key K and the message M, and basically it's just do an XOR operation between these two inputs. So encryption is K XOR M, while decryption takes as input C and K, and it is equal to K XOR C. Now, A XOR B, for example, this symbol denotes the bitwise exclusive OR operation of two binary strings A and B. So if A equals to A1, A2, blah, 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 till AL, so an L bit string, and B is equal to B1 till BL, another L bit string, then A XOR B is an L bit string given by A1 XOR B1, A2 XOR B2, so on and so forth until the end, so AL XOR BL. So let's see why the decryption is almost equal to encryption. So we said that decryption is equal to K XOR C. So if but we know that C equals to K XOR M. So if we replace C with K XOR M, we have K XOR K XOR M. And we know that if we XOR K with K, basically it results to 0. So we have 0 XOR M, which is equal to M, because we said that whenever we XOR a bit with 0, it remains the same. So there is no flipping. Good. So that's kind of a proof why the decryption basically allows us to recover M from C of M. Good. So now what is different in OTP? I mean, what we described in the previous slide is almost identical to the encryption scheme that we showed earlier with the modulo 2 addition operation, right? But there must be some differences, because in the beginning of the previous slide I mentioned that OTP is a perfectly secure scheme. Right, so let's see a definition. So a cipher is unconditionally secure or information theoretically secure if it cannot be broken even with infinite computing resources, which means that if we have our malicious adversary Eve that she is trying to break the cipher, instead of assuming that Eve is sitting in front of just one computer and trying to break the cipher, we can assume that Eve, she has access to millions of resources, millions of computers, for example, and she can, with a magical way, she can put down all these computers to run simultaneously with main goal to break a cipher. So if the ciphertext cannot be broken, even with unlimited resources, then we say that it's theoretically secure or unconditionally secure. Now, the one-time pad is a stream cipher with three main properties. First of all, the key stream bits SI stem from a TRNG, which stands for a true random generator. Okay, so we have built some kind of functions that they can mimic the process of truly randomizing numbers and picking almost truly random numbers, right? This is a field on its own, how to create basically true random numbers. Apart from that, each key is used only once, which means that if we have Alice and Bob, that they have somehow exchanged that key, so they both have access to that key. They use it to encrypt one message, and after they encrypt one message, basically they both drop the key. Okay, so the same key cannot be used twice, right? So you use the key to encrypt the message and immediately you trust it. Now, apart from that, OTP has one more property which is really important. The key is at least as long as the message, right? So you cannot use a key that is it has a smaller length than the message that you wish to encrypt, and that's because if you have a smaller key, then it means that in order to encrypt all the bits of the message, you need to start repeating some part of the key. And if you do this, then basically you are losing the randomness that you used in order to create the OTP key for your encryption. Okay, so keep in mind that the key needs to be at least as long as the actual message that we wish to encrypt. Let's see a formal definition of OTP, of one-time pad. So first of all, fix an integer lambda L that is greater than 0. Now the message space M, the key space K, and ciphertext space C are all equal to the set of all binary strings of length L. So this bracket 0.0,1 at the power of L denotes the set of all binary strings of length L. Now we have the generation algorithm that basically chooses a key from the set of all binary strings of length L. Then we have the encryption algorithm that takes as input the key K that was generated earlier and the message M from the set of all binary strings of length L, and the encryption algorithm output the ciphertext C, which is equal to K XOR M. And finally, we've got the decryption algorithm, which is given as input K, the key that was generated earlier, and the message C that belongs again to the set of all binary strings of length L, and outputs the message M, which is equal to K XOR C. So basically this is exactly what we described earlier. I mean how OTP works, but in a more formal way. Good. So perfect secrecy versus computational security. So these are two really important notions in the field. So a cryptographic system is called computationally secure if the best possible algorithm for breaking it requires n operations, where n is such a large number that it is infeasible to carry out these many operations. Keep in mind that with current computing power, we assume that 2 at the power of 128 operations is an infeasible number of operations to carry out. Hence, a value of n larger than 2 at the power of 128 would imply that the system is computationally secure. Apart from that, note that no actual system can be proved secure under this definition, since we never know whether there is a better algorithm than the one known. As a result, in practice, we say that the system basically is computationally secure if the best known algorithm for breaking it requires an unreasonably large amount of computational resources. Essentially, a computationally secure scheme, or one which is, let's say, provably secure, is only secure when we consider an adversary whose computational resources are bounded, limited. So even if the adversary has large but limited resources, she still will not be able to break the system. Now, most schemes in use today are computationally secure. As a result, in this course, apart from OTP, we will be assuming only the use of only computationally secure systems. Now, on the other hand, we have another notion, the unconditional security. So a system is said to be unconditionally secure when we place no limit on the computational power of the adversary. In other words, a system is unconditionally secure if it cannot be broken even with infinite computing powers. So a system is said to be unconditionally secure when we place no limit on the computational power of the adversary. In other words, a system is said to be unconditionally secure if it cannot be broken even with infinite computing powers. Hence, no matter what algorithmic improvements are made or what kind of improvements in computing technology occur, such system will never be broken. Now, other names for unconditional secure that you can find in the literature is perfect security or information theoretic security. Good. So some theorems about perfect secrecy. The first theorem says that the one-time pad encryption scheme is perfectly secret, right? So it fulfills the notion of unconditional security that we just described. And another theorem says that if the tuple of algorithm gen, enc, and dec is a perfectly secret encryption scheme with method space m and key space k, then the method space k, the size of the method space k, needs to be greater or equal to the method space, to the size of the method space m. Okay, this is really important because if you consider that at some point you will wish to encrypt a word that has its largest length, which means that takes all the possible characters from the method space m, then you will have to have a key k that has at least the same length. So if the key space is smaller than the method space, then you will not be able to find such a long key, which means that you will have to repeat part of the key in the encryption process, and therefore the underlying scheme will not fulfill the notion of perfect security. Now, one question that you might be thinking is that, is perfect secrecy with shorter keys possible? Basically, the above theorem shows an inherent limitation of schemes that achieve perfect secrecy. And even so, individuals occasionally claim they have developed, let's say, a radically new encryption scheme that is kind of unbreakable and achieves the security of the one-time pad without using keys as long as what is being encrypted. This above theorem demonstrates that such claims cannot be true. So anyone making such claims either knows very little about cryptography or is just lying. So we need to make sure that we have keys at least as long as the methods that we wish to encrypt, right? Now, some characterization of perfectly secret encryption schemes. So the one-time pad is popularly credited to a guy called Gilbert Vernon, who filed a patent on it, but recent historical research shows that it was invented some 35 years earlier. So an analysis of the one-time pad had to await the, let's say, groundbreaking work of Shannon, who introduced the notion of perfect secrecy. So Shannon created a theorem about perfect secrecy, and the theorem was saying that, okay, assume we have a tuple of 3 algorithms, generation, encryption, and decryption, that compose an encryption scheme with method space m, for which the size of method space is equal to the size of key space, which is equal to the size of the ciphertext space. Then the scheme is perfectly secret if and only if every key that belongs to the key space is chosen with equal probability 1 over the size of key space by the generation algorithm. And for every method that belongs to the method space and every ciphertext that belongs to the ciphertext space, there exists a unique key k that belongs in the key space such that the encryption of M with K outputs C, right? So there must be only one key that can give you this output for that input, right? So you cannot have a different key that will allow you to encrypt the same message and will give you the same output, right? So that is basically the Shannon's theorem, and it's really important and popular in the field. Now, OTP in real life. So I guess that most of you don't recognize that logo. So this is the logo of a chat application. So that is a secure and privacy-preserving messaging app that uses one-time pad encryption. The application is called Zenodo. Just to clarify something, I'm not doing an advertisement here. I'm not involved in any way in the development or promotion of this application. The only way the only reason for mentioning it here is that it was the first messaging application that was able to offer end-to-end encryption between the sender and the receiver, Alice and Bob. Even though nowadays applications like WhatsApp and Viper, they offer this even in a more flexible way. At that point, Zenodo was the only one, and it is using one-time pad encryption. Now, what does this mean that it uses one-time pad encryption? First of all, that we have to exchange keys in person. In other words, Alice and Bob, they need to physically meet and somehow tap their phones, for example, and exchange their keys in an almost physical way. It provides privacy since no one else can access our keys. There's no spam, right? So because if someone wishes to send you a message, he needs to have exchanged keys with you. And we assume, the developers assume correctly, I think, that in order to exchange keys with someone, it will be someone that you know or someone that you trust. So, someone that you meet physically. So you will avoid kind of spammers. And this, of course, implies also authenticity, because you know that someone that is texting you, you have been authenticated because you have met in person. Good, so let's see an example.
Bob here is sending a message to his good friend Alice. He's probably wondering about dinner, but that's probably private, except it's probably not. Excuse me. Unless it's just you and Bob chit-chatting face to face, you're sending messages. They travel through a third party, one you need to trust, because he has your messages and the keys to your messages. But we don't know anything about this man in the middle, like what he does with your keys, your messages, or anything else he knows about you. So your private messages don't always stay private, but mine do, because I use Zendo. And you should too. Here's how it works. Using Zendo starts in person, where the two of you exchange a unique virtual keyring, aka a one-time pad for you cryptography buffs. It's the only way around that man in the middle. Then Zendo encrypts each message while it's still on your phone. Then it can safely travel anywhere before it gets to Bob. When he gets it, he has the only key that can decrypt it. Zendo uses each key only once, so that you have a uniquely encrypted message every time. His eyes only. Why not use Zendo to keep your messaging personal and private? Download Zendo today from your favorite.
Right. So maybe the first thing that you noticed in that video, apart from the fact that it's nicely designed, is that in the video they are talking about Alice and Bob, right? So basically these names, it's not some names that I invented myself. These characters, Alice, Bob, and Dave, are really well known in the field of security and cryptography. The other thing is that they use OTP correctly. So they said that basically Alice and Bob, they need to meet physically, they need to exchange keys, and then they will be encrypting one message each message with a different key. So once they use a key to encrypt the message, they will have to drop that key and then use one of the remaining keys, and so on and so forth, until the keys finishes, and then they have to meet again physically and start exchanging messages again. Good. So we described how stream cipher works. So now we need to move to block ciphers. So in a block cipher, we have a plaintext message M that we will not encrypt bit by bit. Instead of doing this, what we have to do is that we have to split the message into blocks. So in the block cipher, letters are grouped into same sized blocks, so blocks of equal length. And these plaintext blocks are processed together to form the corresponding blocks of ciphertext in a way that changing a single letter in a plaintext block can potentially change other letters in the corresponding ciphertext. So basically we split our message M into blocks of equal length, and then we encrypt each block at a time until we encrypt all of our blocks, and this will result to our ciphertext. So we will have ciphertext of blocks of equal length L, and the entire ciphertext will have equal length as the actual plaintext. So this is the main idea of block ciphers and the difference between stream ciphers. So stream ciphers, they encrypt bit by bit. Block ciphers, they split our message into blocks of equal length and encrypt one block at a time, and then decrypt one block at a time, right? Good. So Playfair cipher. So this is the first historically documented example of what is known as a block cipher, and it was used by the British military through World War I. So let's see how this cipher works. So first of all, we need to generate again our secret key K, okay, which can be any kind of word. So for our example, let's say that we will have we will use the word basketball for our secret key. Now, what is happening is once we generate the key, all repeated letters of the key are removed. Okay, hence in our case, our key from basketball will be transformed to basketl, right? So some letters, the repeated letters, have been removed. Good. Now, the letters of the reduced key are then deployed in a 5 multiplied by 5 array, starting from the upper left corner and proceeding in reading order. Now, the remaining spaces of the array are filled with the remaining letters of the alphabet, except that A, I, and J, here I and J, are treated as a single letter. Now, so you see that our array starts by having our keyword, our transformed keyword, and then continuing by filling out the rest of the alphabet. Now, assume that we wish to encrypt the message, the plaintext message, the Iceman will arrive at midnight. What we need to do is that first we need to group the letters into pairs, but into adjacent pairs. Now, if any of these pairs has the same two letters, we insert an X between them and we regroup them. So let's see how this works. So we need to split our plaintext into group letters like blocks, okay, and into pairs of letters. And if we find a block that has the same two letters, we need to insert an X between them and continue the regrouping with the rest of the letters. So if we do this, we see the blocks that we created. So the first block is TH, the second one EI, CE, and so on and so forth. What I want you to pay attention at is this RX here with the red. So RX was basically RR from the word arrive. Okay, it was RR, but that block had the same letter twice. Okay, so we had to put in the middle between them an X, the character X, and then regroup the rest of them. Good. Now, the other thing that you need to keep in mind in all block ciphers that in case there is an odd number of letters, if the last block basically in the block cipher has not the same length as the previous blocks, then we need to do some padding, right? We need to put some information in order to make sure that all blocks will have the same length. So in our case, in the Playfair cipher, if there is an odd number of letters, we would append an additional X at the end in order to complete the last pair. And by doing so, we ensure that all blocks will have the same length. So now each letter, we need to see how we will encrypt this plaintext, right? So each pair of letters is encrypted using the array that we have here on our left. And we have three different cases to do this. So the first case is when the two letters are not in the same row or column of the array. In this case, what we have to do is that we replace each letter with the letter in its row that is in the column of the other letter. So in our example, the first letter is TH and falls in that case, right? So let's try to find basically the row of T and the column of H, right? And then basically, if we want to encrypt the letter T in our first block, this will result to the character L. And then we do the same for H, which will result to the character G, which means that the encryption of our first block, which is equal to TH, will be the ciphertext LG. And this is the first case where the two letters are not in the same row or column of the array. Now, the second case is when the two letters are in the same row. In this case, we replace each letter with a letter immediately below right, cycling back to the beginning of the row if the letter is all the way on the right, if we reach at the end of the row. So in our example, the pair IG basically falls into that case, and it gets encrypted to MH. Now the last case, case 3, is when the two letters are in the same column. So in this case, we replace each letter with a letter immediately below it, cycling back again at the top of the column if the letter is all the way at the bottom. In our example, the pair LA falls in that case, so it gets encrypted with HL. So LA gets encrypted with HL by using this rule. By moving on and doing all the encryptions for all the blocks, basically we end up with this ciphertext. So we just used Playfair and the rules that we just described in order to encrypt the word. The sender, the Iceman, will arrive at midnight, and the ciphertext is this series of characters at the bottom of your screen. Good. So from history to reality, I forgot to say that the decryption process in Playfair cipher is basically is accomplished by just reversing the encryption procedure. Now, from history to reality. So as I mentioned, Playfair is a historical cipher, right? It's not the cipher that we really use in our daily lives, and it's not secure to use anyhow. So the 20th century saw a proliferation of ever more sophisticated block crypto systems that required special mechanical or electrical devices to use. These systems continued to evolve into the computer age, and data encryption standard, DES for short, was developed by IBM and adopted by the US government in order to address the growing cryptographic needs, not only for the industry but also for general businesses. Now, the encryption process of DES involves 16 complicated rounds of processing blocks consisting of binary strings of size 64. So the block size of DES is 64, while the key of the length of the key is 56. Now, the details of the algorithms are quite complicated, involving various substitutions and permutations. Keep in mind that Playfair was a cipher that we could use with a pen and paper, as we did in the previous slide, while DES is a computer-only system, which means that it is unfeasible for hand calculations. In addition to that, DES has a high degree of entropy, meaning that small changes in the plaintext can produce radically different ciphertext. The system was in widespread use for nearly 30 years However, with increasing computer speeds and power and new cryptanalysis methods being developed, it started to become apparent that a more secure system was required. And this basically led to the development of the Advanced Encryption Standard, AES for short, that was done in 2002. Now, keep in mind that while DES was developed by IBM and further enhanced by NSA, I think, AES was developed by a team of independent cryptographers. Whereas the DES, although quite complicated, relied on rather basic mathematical functions and operations, the AES is based on arithmetic in finite fields. In this course, every time that we use or assume the existence of a symmetric encryption scheme, we will be always assuming that this is an AES implementation, unless if otherwise is mentioned. Now, AES is using a block size of 64, like in DES, but it comes in 3 different flavors with 3 different key lengths, 128, 192, and 256. And of course, it also has a high degree of entropy. So that's about it. So I think that you got a quite a nice overview of how symmetric encryption works and the basic concept of it. And now we are ready in the next video to move on to the description of asymmetric encryption. Thanks a lot.